All right, are we ready to get started?
Mm-hmm.
So welcome everyone to our AI seminar. Today we're going to have a talk from Kristina Lerman, who is at USC, the Information Sciences Institute. Her talk is about algorithmic integrity and the predictability limits on human-centered AI systems. Kristina is a principal scientist at the University of Southern California, ISI, and holds a joint appointment as a research professor in the computer science department. She's trained as a physicist and now applies network analysis and machine learning to problems in computational social science, including crowdsourcing, social network, and social media analysis. Her recent work on modeling and understanding cognitive biases in social network has been covered by the Washington Post, Wall Street Journal, and MIT Review. Before I give the floor to Kristina, just a couple of things to remember. If you are a panelist, you can turn on your microphone and ask questions live, or use the chat if you want to use that feature. If you're an attendee, please use the Q&A. Kristina, thank you.
All right, thank you, Deborah. Okay, all right, so everybody can see my screen, right? Let me just set that up once more. All right, thanks, Deborah, for the introduction. Let me also, oops. Sorry, just give me a second. I need to close the Zoom thing. So if anybody has any questions, please type, or somebody can say it in audio, because I'm not going to be seeing the Zoom. But thanks for joining me. I'm really looking forward to trying out a new talk. This is a brand new talk that I created just for this occasion. It sounds maybe highfalutin, but I'm trying out some new ideas that I've been working on the last few years. But this is really the first time I'm bringing all these ideas together to give in a talk format. So I really look forward to your comments. I hope you give me some feedback, what ideas work, what ideas don't work. And well, okay, let's start. All right. So for, AI has been, now everything is AI. You can't open up a newspaper without reading about AI. And AI is, holds a great potential, So so from an optimist viewpoint, this is how AI systems work. They ingest AI algorithms ingest lots and lots of data, sometimes supplemented with some ground truth from humans to provide some training examples, of what is good in the world, what the humans' view of the world. And then the gears of an AI algorithm churn, and spit out answers. And, the answers are fantastic. AI has really transform the world, and making things that almost seem like magic. AI has been used to bring order to the web, because of AI systems and various personalizations that I'll talk about later. We can never get bored ever again. AI, there's all this excitement that AI can be used to solve the thorniest, hardest world's problem. And of course, AI has been used by many to make money, and lots of money, so this is the optimist view of the world. But recently people have been focusing on kind of the dark side of AI. Many things within this process can go wrong. The training data, AI ingests lots and lots of data, but data can be biased, it can be incomplete. How does it affect learning? We don't yet know. Human experts or annotations that people are providing to train AI systems, well, they could be noisy, they could be incorrect, that could be reflecting the biases and prejudices that exist in human systems. And how does AI inherit all these biases, and how does it affect the applications and recommendations of AI system creates? Of course, a lot of emphasis recently has been on how these types of biases, either in the training data or in the data that's being collected, how it's actually making AI create predictions that cause harm actually to some groups of people. AI fairness has become a big research area, right? And justifiably so. So this is one problem. But another problem that is starting to receive more attention, perhaps, is that then when AI makes recommendations, these recommendations flow back to the humans, to the social systems, to create more data that will be used by AI to make its actions. So this actually creates a feedback loop. And what is the impact of this feedback loop on the behavior of AI algorithms? Nobody knows yet, or people are starting to realize that that could be a problem. So my talk is going to maybe take this kind of pessimist view. I don't want to be a pessimist, but in order to enable the optimistic vision of AI, we need to guard ourselves against this pessimistic aspects of it as well. So I want to focus on kind of the threats to the integrity of AI-driven human-centered systems, what I'll call socio-technical systems. And I'll just talk on this, by no means a comprehensive or exhaustive list of problems that can arise, but this is the problems that I have addressed in my work, and I will show you how this affects integrity of AI algorithms. So the first issue I want to examine is heterogeneous data. The fact that AI algorithms are trained on very diverse data that comes from different individuals and different behaviors. Traditional statistical models that ignore these differences will create wrong results. There'll be models will be non-reproducible. Results will be biased. Another issue that has not received that much attention yet is that the AI systems algorithms are trained on data that is incomplete. Many systems, especially human social systems, are only partially observed, and this actually can reduce the accuracy of the forecasts and the predictions that the AI system makes, any AI algorithms makes. There's some fundamental limits to predictability due to incompleteness of the data. And lastly, there's also something that has not received that much attention, is that algorithms themselves can be unstable. By the instability, I mean that feedback can amplify small fluctuation and freeze them and create large differences in the outcomes, and which differences can be unfair as well. In fact, I will be so bold as to say that algorithms can be chaotic, and algorithmic chaos should be a problem we should be considering. So this is what I'll be discussing. These are the problems, and I'll be discussing specific aspects of these problems and with applications. So I will talk about, show how heterogeneous data can impact statistical algorithms and their performance. And I will highlight specifically with an example about estimating COVID growth rates that everybody should relevant for the current situation or current human condition. Then I will talk about limits of predictability of partially observed systems, how having incomplete data can affect forecasts we make of human social systems. For example, how popular some topic will become on social media, topic described by its hashtag. And then I will, finally, I'll talk about some very recent work on algorithmic instabilities that is actually ongoing. So some of the, a little bit older work about ranking stability of crowdsourcing systems, and then some very new hot of the presses work that talking about instability of recommender systems. Okay, so let be the three parts of my talk. Act 1, heterogeneous data. Actually, I have been gratified to see that heterogeneity is justifiably receiving some attention. This is from the paper that was just appeared a couple of months ago in Nature Human Behavior. They're talking about behavioral science is unlikely to change the world without a heterogeneity revolution. What they really are talking about, actually, this twin findings that recently, we all heard about this crisis of reproducibility in science, especially in the social sciences, and talking about actually the fact that we have lots of data and data is highly heterogeneous. So first, I would like to define what heterogeneity means, so we are on the same page. So heterogeneity is a non-random explainable variability in the direction and magnitude of the effects, statistical effects for individuals within a population. And so this heterogeneity actually affects analysis of scientific data, affects analysis of any kind of data in data science. And this effect of heterogeneity are really being explicitly appreciated only recently. But let me walk you through how it might affect what is now called the crisis of reproducibility, how it might affect this. So suppose we have some study, the study wants to measure some outcome. Let's say Y could be, for example, how many words a minute the person is typing versus some explanatory variable X, maybe X is heart rate, or could be, how many calories the person of food person has consumed a day or something. So some participants are recruited for the study. Here the dots correspond to participants, and you measure your outcome as a function of this explanatory variable, and you get do linear regression, some statistical analysis to find the data. And in this particular case, for example, they'll find that there's a red slope, there's a positive relationship between the explanatory variable and the outcome. Suppose next time when the same studies, somebody wants to reproduce this, another group wants to reproduce the study, they recruit participants, but they oversample this middle group of participants. Then they're going to get a completely different effect. They say, okay, there's actually not much of a relationship between outcome and explanatory variable, right? So what has changed? Well, what changed is actually nothing has changed within the individual groups. So what is going on here? This data actually, the reason they found the effect was because the data is heterogeneous. It actually consists of underlying groups that have different behaviors, which are shown here. And as you aggregate the data, you're measuring the outcome as a function of the explanatory variable for the entire population. Your properties of the population change. First and here, the properties of population change with respect to this explanatory variable. When you're on the left here, low values of the explanatory variable X, you have mostly this first group. But as you go to the right, actually, the group drops out, this lower group drops out, and you only get the higher group. So next time you run the study, the groups have the same behaviors, nothing has changed, but you've oversampled one of the groups, and this actually changes the characteristics of the entire population and gives you what looks like an unreproducible result. But in fact, if you had accounted properly for this heterogeneity, for the existence of these groups, then you would have seen measure the proper behavior, and you would not have actually seen what appears like an unreproducible result. Okay, I see questions, maybe something in chat, but I'll ignore it for now. If there's a question, please, try somebody ask it, or via the audio.
No, I might just
Okay.
mention, if they have questions, to use the Q&A feature or open your mic if you're a panelist.
Okay, thanks. All right, so, and this is actually not a new, it's not something new. People have known this, of course, for a long time. One of my very favorite papers on this topic is from 1995 and gives many examples about how heterogeneous data can bias analysis. So one of my, this is a really compelling example. That's why I use it in my talks. Suppose actually you have a study done to measure how recidivism, recidivism means when people are served their time in prison, they're released from prison, how often do they recidivate? How often do they commit a crime and have to go back to prison? So, and the study also looks at the recidivism rate, mu, versus time, starting from the point when the person is released from prison. And if you analyze all the data, actually, you see that the recidivism rate decreases in time. What does this mean? Well, this means people are less likely to commit crime over time. What can you infer from this? Well, people inferred, as people age, as they become older, then they are less likely to commit. They somehow become more peaceful and less likely to be criminals. But is this actually true? Well, actually, there could be another effect that could be affecting this data. Actually, in this particular case, the characteristics of the population could change as a function of your explanatory variable time, leading you to different conclusions. And in fact, what actually is going on in this data, that there are actually two latent subgroups, two subpopulations with different behaviors. Let's call them incorrigibles. Once they're released from prison, they commit crime at some higher rate, and they go back to prison at a higher rate. And they're reformed once they're released from prison. They're not very likely to commit a crime, or they'll be so they go back to prison at some very, very low rate. And as a function of time, actually, as we got here, these people, the incorrigibles, they commit crime and return back to prison. There is fewer and fewer of them with the population. You're getting more and more people from this reform group within the population. So overall, the recidivism rate for the population overall is declining simply because the characteristics of the population are changing. And this is actually a very pervasive problem in data science, and this is something we see all the time. For example, when we're analyzing Stack Overflow, this is a great site where you can ask questions and other people can answer them, and then you can select what the best answers are. And here we were simply looking at what is the probability that answer is accepted as the best answer to the question as a function of position when the user wrote the answer. Was it the first answer of the session, with the second answer, third, and so forth? And what it looks like, actually, it looks like answers are, answer quality, answers are becoming better over time. As you can construct all kinds of hypotheses. People start answering questions. Maybe their first answer is not so good, and then they get warmed up, they get going, and they write better and better answers, so they're more likely to be accepted as the best answer. Well, actually, it couldn't be farther from the truth. The reason you get this upward trend is because your population, it's heterogeneous. The people who are writing these answers here, who have written 15 answers, are very different from people who have written 1 or 2 answers. And you can actually see this in this other plot where I've simply taken the same data that we used to create this plot. I've taken the same data and disaggregated it by the length of a session, meaning how many answers people write. So people who write only 1 answer and then they leave, go away, do the rest of their life before, is so here they're actually not very good at answering questions. Their answers are not that, relatively less likely to be accepted as good answers. People who write 2 answers before they leave, look at their first answer is actually better than their second answer. And people who write 5 answers, the first answer is better than the second answer, so forth. So overall, you see people actually get worse over the course of a session at answering questions. But why do we get this top effect? Well, because of this, even though people get worse, there's some heterogeneity so that people who can write and do write more answers, answer more questions, their answers are better. And because their answers are better, once these poorly performed people drop out, the overall performance curve is pulled up by these people who are really good at answering questions. Okay, and we call this kind of ego depletion. We are inspired by Roy Baumeister, who's written, he's a psychologist who's written many papers, done many experiments showing that willpower can be thought of as kind of a finite resource that gets depleted. So for example, if you do hard mental efforts like answering math questions, it leaves you with fewer resources to exercise willpower and self-control. So people who've, for example, answered hard math questions, they're less likely to resist impulses like being offered chocolate cake and say no to a chocolate cake, or being able to keep their hand in a very, very cold water for long periods of time. And it is ironic that actually Roy Baumeister is a kind of controversial figure in psychology because people other groups have had hard time replicating their studies, which could be again because of the heterogeneities of the populations that both people are, those different studies are experiencing. But we see this kind of cognitive depletion, which is completely in line with Roy Baumeister's work. We see it in many, many different, we see it all over the case. Every single system we looked at, Facebook, Reddit, Twitter, Stack Overflow, Khan Academy, we see the same kind of signature of cognitive depletion that Roy Baumeister was talking about in psychology. So for example, like in Reddit, if you look at comments that people posting on Reddit and you break people down by like session, how many comments they post, then you see everything is actually declining over time. So you can see, look at how long the comments are, it goes down. how many votes, like on Reddit, people can upvote good comments and downvote bad comments. So we can look at the score of the comments received. It also declines with time. Like the first comments you write in the session are better than the second comment, and better than the third comment, and so forth. You can look at how many responses comments received. They also receive fewer responses over the course of sessions. And readability as well, how easily, textually complex it is, also declines. So this, you can say, like, once you account for heterogeneity of the user populations, once you account for differences, the people who are dedicated Reddit users, they answer many questions or make many comments, versus people who are not so dedicated, they only answer one, write one comment before they leave. Once you account for this heterogeneity, and then you get this replicable, reproducible results that show the same effect, which is cognitive depletion. People somehow wear themselves out by activity, and the quality of their performance actually decreases over the course of the session. Okay, so I just this is previous work. I want to show how heterogeneity actually does have other effects, So here is an interesting case study that actually Keith Burkhardt and Fiona Goa had done. We're looking simply at COVID growth rates in the US. We are measuring how quickly case numbers and deaths grow within the pandemic. So this is actually data for 2020 from New York Times, which has a good COVID tracking thing. And you can see actually there were 3 surges in the US as a whole, and we are actually measuring just the growth rates of these surges. We can estimate the exponential growth rate using negative binomial regression. And actually the paper just appeared online from the Philosophical Transactions. Actually, really great paper. It has many other things like trying to explain the unequal impact of COVID. But here I'm just going to be focusing on aggregation, on bias that comes because of aggregation or heterogeneity of the data. Okay, so there's this growth rates, and we can actually estimate growth rates for different geographic units. For example, New York Times website presents at the level of counties. So we can measure growth rates in this manner for the individual counties within the United States. Then we can aggregate all the counties within a state and measure the growth rate for the state as a whole. And finally, we can aggregate everything, all the data for US as a whole, and measure growth rate for the nation as a whole. And what you find when you do this is actually that the estimated growth rates for COVID and death rates as well that you estimate using this method, they're higher at larger spatial scales. So it looks like, so here I'm showing distribution of the growth rates for individual counties in blue. Purple is actually when the same data that was used to generate counties, when the same data is aggregated to estimate growth rates at the state level. And this line is actually when all the same data is aggregated for US as a whole. And this is what we estimate, the estimated growth rate. Yes. And you can see that the COVID appears to be spread more quickly in states than within their underlying counties. And also more quickly spreads more quickly. The growth rate is higher for the nation as a whole than for actually most of the counties within the country. And there's a reason for this, actually, because actually we'll explain more in this next slides, is because of the data is heterogeneous. Some counties have very high growth rates, some counties have very low growth rates. So there's hotspots that have high growth rates dominate the statistics and they skew the overall growth rates. So you can actually see some of this here. Actually, here I'm showing growth rate of COVID within New York State. This is the black line, and this is within the counties within the New York State. And the counties that make up New York City actually basically dominate the statistics. So virus grows exponentially in each county, but the rate varies actually. Some grow faster, some grow slower, and actually the denser regions, we do find that denser regions, actually denser counties grow more quickly. And also virus arrives in each county at different times. So early arrivals also are associated with faster growth rate because, perhaps because they predate mitigation measures such as mask wearing and others. And so these kind of the places that started earlier and are growing faster, actually they dominate the statistics. But of course, as you measure the growth rate, and by the way, you cannot account for this. You can get correct growth rate for the state if you do simply weighted average. And why not? Because as you measure the growth rate as a function of time, different counties actually contribute at different rates to this overall average, or to the overall growth rate for the state. So skewing it, systematically skewing the measured growth rate. And this actually, there's, should probably speed up a little bit so you can actually see this. This is true for the first surge. It's true also for the second surges as well, and for a third surge, the summer surge as well. You actually get growth rates overall decrease, but you still get the bias, the aggregation bias, where growth rates for counties are systematically lower than growth rates for states and the growth rate of COVID for the entire country. All right, so I have some more things to consider, like each to talk about. So if you have questions, let's leave them till the end. So I want to talk about this, how the impact of incomplete data on the predictability of socio-technical systems. Okay, so why is this question important? Well, actually, human systems are really difficult to observe. It's really hard to measure what people are doing, whether it's social media, even social media, which you think is entirely observable. If you really want to study it systematically, we get Twitter decahose, and it only provides 10% random sample of tweets. For example, you can have, you know, all the tweets that are created. You can only, well, I shouldn't say you can only, but generally, if you want to observe, you know, Twitter through what the APIs that they provide, you can, you know, you will only see some fraction of all the tweets that are possible. But it's also true of other things, you know, stock market, maybe epidemics, you know, maybe you don't have full-scale monitoring, as we're seeing right now with the Omicron variant. You know, there's surveillance, there's barriers and challenges to surveillance. You might not observe all the data, all the infections that are occurring. Cyber attacks, this actually arose from this whole research area arose from the project we had to predict cyber attacks, and we basically failed to predict any cyber attacks for this very reason, that, you know, we're leaving out a lot of the data, a lot of the cyber attacks that are unsuccessful are not being observed. So the question we had actually, how does this affect us? We can only observe some of the data, not all. How does this partial observability bias the models learned from this incomplete data? And specifically the question, especially in the cyber attack forecasting, we were grappling with the question, you know, can we accurately forecast processes that are not completely observable? And actually the answer is no, but let me walk you through the steps. So you can actually, the simplest way to kind of grab a handle of this mathematically, we need to define what partial observability means. And one way to define it that actually allows us mathematical analysis is to think of partial observability as filtering or sampling data. So we have some process, dynamic process X. Suppose it's like number of volume of events, daily counts of events, whether it's number of infections with COVID, or maybe it's the number of tweets that are being generated each day, or the number of cyber attacks against an organization that are occurring over day. So this is the X, process X. But what observers see is actually some sample of the events. We don't observe all the events. We only observe some events. Let's call those time series of those events, let's call it Y. And for simplicity, let's model that each event has some probability of being independently observed. Let's model it by binomial distribution. So we have some filtered signal Y that is basically kind of Bernoulli distribution of signal X. So X with some sampling rate P. So let's say each event has probability P of being observed, and you do it independently for each event. So then P is the rate at which events are actually coming in after filtering. So starting with some time series, if this is volume of events, if each event has only probability P of being observed, we might get a different time series, which is Y. Here I'm showing actually if you 10% sample these events from the generated this time series, we sample these events at 10% rate, you actually will get some different looking time series. And then we are asking, then how can they actually forecast with incomplete data? So forecast in general has this mantra that the past is the best predictor of the future. And this is a good rule of thumb to have, except when the data is not complete. So you can actually ask them, like now that I've set up mathematical framework, we can actually ask how well can the filtered signal Y predict the future signal Y? And the answer is actually poorly, especially as we lose more and more information due to filtering. And I'll show you this mathematically as well. And then I said, okay, we might be losing some signal due to filtering Y, but suppose there's some other external signal Z. And they actually spent 4 years in the COS program, this cyber attack forecasting program, looking for such external signals that might help, these external signals that are highly correlated with this process we are not observing. So can this external signal recover information lost to filtering? And the answer is actually no. Even this loss of information you get from filtering is irrecoverable. So because we are doing this mathematical analysis, first I want to describe, define how we measure predictability. We can also measure it within the forecasting task, but we can quantify predictability of a time series. And actually there's 2 different approaches. We tried both of them. One of them is simply to use autocorrelation. So this autocorrelation is simple Pearson's correlation between a signal and its lagged values. So you take Y at some signal Y at some point in time and Y, for example, 2 days earlier. And you measure correlation between the signal, and that is the autocorrelation. People have lately introduced this more model-independent measure of predictability of time series. It's called permutation entropy. We're given some time signal, you construct little chunks, you chunk it up into different segments of different lengths, and you just simply do the statistic. You count how many segments, for example, do increase and how many segments have this go up and go down. And you basically enumerate all possible ways you can have the segments. You enumerate all possible segments, shapes, and then you count how many of each shape you have. And entropy of those counts gives you permutation entropy. So that's another way people have used to measure predictability of a time series. And what we showed mathematically in the paper that sampling actually impacts these measures of predictability. Specifically, we showed for autocorrelation, you can actually show that autocorrelation decreases with sampling. As you see, this P is probability of observing each event. So as P gets smaller, so you lose more and more of the signal, your autocorrelation actually drops as a square of the sampling rate P. And also we have another formula that shows actually that correlation between the observed signal Y and external signal Z, and when Z is highly correlated with X, the correlation between Y and Z also decreases with sampling rate. So this external signal does not help you recover lost information. And we actually validated this empirically using data from Twitter. We also did it for epidemics, and we also did it for validating cyber attacks. And I'm only showing predictions how loss of predictability affects predictability of hashtag popularity. So we can, using time series, we have actually used the search API to get all tweets with specific hashtags. So we know how many people are talking about specific topic. And these lines actually are showing the relative autocorrelation of these time series for over 1,000 different hashtags as a function of sampling rate. Suppose we can simulate what happens if we only observed some fraction of the actual tweets and not all of them. And you can see for many hashtags, for overall, actually you do the autocorrelation of the time series, of the sampled time series actually does go down. And the loss of this autocorrelation means the signal the hashtag popularity becomes less predictable. So autocorrelation goes down, permutation entropy actually goes up, but then permutation entropy means the higher the entropy means less predictable the signal is, more noisy it is. So both measures of predictability, of autocorrelation, and permutation entropy show that they actually do, in real world time series, you do decrease predictability of this time series with sampling. So as the sampling rate increases, you see less and less of a signal, actual original signal itself, you actually lose predictability. Okay. All right, so my final topic is going to be about algorithmic instabilities. And unfortunately, I'm going to have to speed up. I thought didn't bank the time as well as I should have. Okay, so first I'm going to talk about crowdsourced ranking, and this is actually a very simple algorithmic type ranking that actually is used by many systems to discover popular content. So, I just did a screen cap of what Netflix homepage shows you. And one of the lines, one of the things it presents is actually what is popular on Netflix. So it orders movies by popularity. So you can see what people all over the country like. But this is a very common technique for called crowdsourced ranking, which aggregates decisions of many people to rank items. And this belief is that best items will float to the top. So here, best, House of Cards, as I get, is a very, well-made TV series, and many people liked it, so it must be good. And this is used by many other platforms, Twitter, Reddit, Stack Overflow, which we actually we study Stack Overflow quite a bit. And there is that belief that best, I told you before, in Stack Overflow, people ask questions and other people answer them, and best answer is supposed to float to the top as people select, what they consider are good answers. And this is because this is such a popular crowdsourced ranking, such a popular thing being used by many different platforms. You can think New York Times bestseller list, Billboard type musics, the movies, blockbusters. Everybody relies on this crowdsourced ranking, that it actually has received lots of attention from researchers. So one of the seminal studies in this area was done by Slganik, Dodds, and the Bots that looked at the instability, that showed that there's instability in the popularity of rankings, how few items become runaway hits like blockbusters, but most items actually languish in obscurity. And they showed that you actually cannot predict which becomes the next blockbuster, which becomes the next hit. And this is actually was very clever series of experiments that we actually borrowed their design to do our own sets of experiments. So they created this online experiment that replicated the cultural market. So users were shown a list of songs that were ordered in some fashion. And you actually had these two experimental conditions. In the independent experimental condition, users were shown songs and they were randomly sorted in random order. And in the social influence condition, the users were shown songs and they were ranked by popularity, and they showed how many downloads the songs received. So download was actually used as a measure of popularity. If user download song means they liked the song, and they measured how many downloads the song received as a measure of its popularity. So they sorted them according to the number of downloads, and they showed the downloads, because in their minds, actually, the Music Lab study was looking at the impact of social influence on stability of rankings. And there also another important thing to note is they defined, in these types of cultural markets, it's really hard to know what the underlying quality of a cultural item is, like a song. What is the quality of song? You know how to measure its popularity, but what is its underlying quality? It's subjective, it's hard to measure. So they simply operationalized quality as the popularity under this independent condition. So in the random condition, if people more or less saw, the same number of people saw the songs, the more popular songs probably were of higher quality. So they used this measure as a measure of quality. And what they find is actually that the ranking is unstable. There's a huge difference. And by the way, also another important thing is that actually you can run this experiment again and again and again, starting from the same initial conditions where songs don't, have 0 downloads. You can run it again and see what happens, which songs become popular or not. So each time they run an experiment, here's like I'm showing results of 2 experiments where you show like the ranking of this song in the social influence condition versus its rank in the independent condition. Basically, this is popularity in social influence condition versus its quality, song quality. And you actually see huge differences in popularity, like the same song, which has similar quality, I guess. It can be either ranked very low, or can be ranked really high. So few items can become extremely popular, while most don't. And popularity is only weakly correlated with the underlying quality. So you can notice actually there's a correlation. You know, it's in the best and the worst songs actually stay in the same positions, but in the middle, anything can happen. You know, a song can be, in one experiment, can be a kind of intermediate quality song, can be really unpopular, or it can be very popular. So they wrote this paper that said, okay, social influence, you know, creates inequality, reduces predictability, but actually the story is more complex than that. So it's true that popularity-based ranking freezes early advantage, and creates inequality and unpredictability of the outcomes. But you can have many different things besides social influence affected. So this is actually several experiments we have done. This shows that position bias, the fact that people pay more attention to items at the top of the list, serves to freeze in these early advantages to some songs and freeze them, making them very popular. Social influence actually amplifies the effects of position bias. Also, we showed that cognitive load, for example, if on Stack Overflow, the more answers there are, the more position bias will play an effect in users' judgments of which answers are better or not. And it also applies to this clever experiment that Keith has done. Can show even when some answers are objectively, we know they're objectively better than others, they can still get stuck you can still have better answers get stuck in lower positions and never get to the top of the list within popularity ranking. So this is what we identified as actually what we call algorithmic instability. So this is a set of experiments, and actually we know that there are some answers that are objectively better because within the experiments, users were asked to answer mathematical questions. Correct answer exists, but it was not easy. You know, for example, we said, oh, okay, what is the ratio of the large shape to the small area of the larger shape to the smaller shape? You know, we know the correct answer, but it's really hard to say. And what we find actually, look at this, there's this instability in the regime where if you, based on like, you know, some answers, this is y-axis is a quality difference between these 2 answers. And this is effect of position bias. So objectively better answers in this regime actually will always rise to the top and be in the top position in the popularity ranking. But in this regime, they're not objectively better answers are not guaranteed to rise to the top. And they can be, sometimes they can get frozen in the lower positions. When does this happen? It happens when there is actually, like, for example, if you go down, actually the better answers are less obvious, like quality difference is small. So the better answers are less obvious which one is the better answer. So as you go down, actually, this popularity ranking is unstable and better answers doesn't always rise to the top. Or when position bias is higher, when people pay more attention to the top answer, regardless of, you know, what is in the top position, like popularity ranking is also is unstable, which means the better answer will not guarantee to get the top. Sometimes like if the worst answer accidentally ends up in the top position, it will get frozen in that position. It will never be replaced by a better answer. So this is actually the problematic regime in which a ranking will not produce what is objectively an optimal solution. So that's for this crowdsourced ranking, but lately we've been looking actually at another algorithm, performance instabilities within algorithmic recommendations. And this is very new work that Keith Burkhardt is doing. So we're looking actually at this particular line, for example, the personalized recommendations. When Netflix, for example, is picking movies that it thinks you will like and recommending them for you. So what Netflix is doing, and this is actually the basis for many other personalized recommender systems, is trying to learn your individual preferences based on what other people are doing as well, and update, and it actually and present things for you, the things you will like, and then based on your feedback, what movies you do end up watching and liking, it will update the model it has of you. And you can ask actually whether these preferences can be reliably learned. And we studied this system, this actually stability of the recommendations algorithms within this model recommendation system to understand how user feedback, how this like loop of where users actually act on the recommendations of the algorithm, and then the algorithm is retrained on these user actions, how this feedback loop affects algorithm performance. So we created a bunch of agents that had individual preferences, and these agents can then act on what the system provides, and then we monitor evolution of the system as a whole. So this is actually this model of the recommendation system that Keith implemented and studied. So it has two parts. So it has agents that have, so these agents are described by the teacher model. So these agents have preferences. This is by the blue vector. And there's items that have their inherent like abilities. You know, this is the orange vector. But sometimes we also want to introduce the degree of like stochasticity into the system, because sometimes people might just choose whatever items recommended regardless of their individual preferences, just simply because they're bored or because, you know, they're curious, you know. So agents act on just the recommendations, or maybe because, you know, the item appears in the top position, so this model's position bias as well. So with probability beta, agent will choose whatever is recommended, regardless of its, you know, preferences. And with probability 1 minus beta, the agent accepts recommended items according to the preferences, right? And we can actually look at the user item matrix, and we can sum the columns to count, you know, what the inherent choices of, you know, of agents are. And then the other part is the algorithm. This is described by the student model. The student model is trying to infer these preferences of the agents using the matrix factorization. So it observes, like it looks at all the agents and their items, looks at what items the each individual agent chose, and then it tries to learn the individual preferences of the agents using matrix factorization. And it does it in a loop. You know, agents then act on those and gets the new use agent item matrix, does matrix factorization again, and does it iteratively until all items have been seen. And we can actually look at how many agents chose a particular item, count this number of black squares, for example, for a particular across all agents for a particular item, and that will be the item popularity. So we can actually measure how the outcomes, how item popularity changes over time. So the first question we want to ask is, how well can this hidden teacher-student model describes agent preference, how well it can be learned? So here this actually describing correlation between the teacher model and the learned student model across all elements of the matrix. So it shows a correlation over time. And you can see correlation is actually less than 1. So it will never be perfectly learned, but correlation does increase as an algorithm sees more and more data, it does get better. But as long as there's, so more data does improve learning, but it depends on the amount of stochasticity in the system. So when learning is harder, because when users' choice only partly revealed, then correlation actually drops. So for blue line is for higher value of beta, when the agents are paying more, like not paying attention to their own preferences, but acting on the recommendations simply, then you have much harder time learning. But this is overall matrix. We can also ask what happens. Okay, we cannot learn, maybe we cannot learn well what all the items, what user preferences across all the items are, but let's see if with the each user's top item, the best item they most like, how well can the model actually reproduce it? And again, you see actually there's very huge little correlation between item popularity learned by the student model and the underlying. This is actually underlying items actual popularity within the teacher model. So actually, you can see actually there's a huge, like, what if the student model was correctly learning, then all the points should fall on this line, on the diagonal line, but item popularity can be anything. Actually, it can be some items can be either non-popular or very popular, and with higher values of beta, the more noise there is, actually there's going to be huge variance as well. There's more. And
Kristina, just giving you a minute.
Yeah, I need to. Yeah, this is actually to run up. You can actually look at the top item and see when does it become the most popular. And you can actually see this is across many different runs of the algorithm. Sometimes the top item that ends up being the most popular, sometimes it's most popular early on, sometimes it's very late. And actually the best item will eventually become popular, but the time when it emerges as more popular just changes a lot. So this is actually evidence of instability of recommendation systems. So a slight change in initial conditions, like just as stochastic noise, leads to large outcomes, changes in when the item become in the outcome, which is like, when does the item emerge? Does the best item, and this actually would argue this is evidence of algorithmic chaos. This is the fact that sensitivity to initial conditions, the fact that small changes in initial conditions can drastically change the long-term behavior of the system. This is the hallmark of chaos that is very common. For example, in the weather systems are known to be chaotic, where you can have the butterfly effect, where like just a small change initially can have large changes overall in the overall long-term evolution of the system. And this is just one example of the recommendation system, but I believe it's inherent in all socio-technical systems overall, that they're inherently unpredictable. So the question then arises, how can we trust unpredictable systems? Or do we need to live with unpredictability and design human-centered systems with this unpredictability in mind? And this is actually all I had to say for now. There's some key papers that describe these concepts, and of course I want to thank my collaborators and the sponsors. And I'm sorry we only left 5 minutes for questions, but I look forward to hearing your questions.
Thank you, Kristina. If you have questions, please put them in the Q&A or raise your hand if you're a panelist, or put it in the chat. Abigail?
All right, can you hear me?
Yep.
So many interesting topics. I'm trying to take it all in, but I have a question about the first example in your recent paper with Keith and Fiona on the COVID data. And there was a great question in the chat about there are, when we talk about heterogeneity in COVID data, there are so many different sources of this heterogeneity, and this can also be in the way that the data is collected and aggregated, right? And so there are different ways of defining infection. There are different testing rates in different locations based on how many people they have coming in to get tests and how prevalent their testing centers are. And then there are different ways that the data can be recorded, right? Like if the data is it's averaged over time, those kind of things. So all of those factors could play out in the COVID data. But I was thinking that the example that you provided when you are comparing different rates within New York State was a very good one for getting at the type of bias that you're exploring here, because there are likely to be more consistent definitions for how data is collected and more consistent ways of recording that data across these different counties within New York State. And so I was just wondering if you were able to explore that or not, and then more generally, if just in terms of, because there are all of these different heterogeneities in the data, if what's the process for being able to identify the contribution of one kind of heterogeneity versus another on these biases? Or maybe like, how do you take out heterogeneity and because what you're interested in, right, behavior within homogeneous population. This is an open research question, and this reminds me of MRI scans, for example. There was an effect that
which machine you use, there's affects the scans that you get. So some of the effort has been trying to get rid of this nuisance effects to learn a fair representation image that is independent of the actual instrument that you use to measure the data to get this MRI scan, to get to the actual structure that MRI reveals. So I think we need something like that for data science, kind of get some independent of measurement modalities. We want to get the actual process, see the actual process independent of how it's being measured. So I think there's lots of interesting questions like the ones you're highlighting, but it is important because of the heterogeneities. Like if you do simple-minded like aggregation, you might get really wrong results. So
right.
Yeah.
And just a point on getting at that process. I know with epidemic models, like if we do multi-population models that look at interactions within subpopulations, like within each county in New York State and also across those counties versus a single population model for New York State, the multi-population model will always give these lower reproductive numbers, if you're estimating a reproductive number, than the aggregate level. And so, yeah, it makes me wonder how much is coming from the data and how much is coming from the process or like the assumptions of the process in the model.
Yeah, I would love to explore these kinds of questions. Yeah, this is exactly the questions about the basic process of measurement that are really fascinating to me.
Yeah, cool. Thank you.
Thanks, Abigail.
We have one more question with Aram.
Hi, Kristina. Good to see you. And good
Hi,
to hear you. Yeah. So yeah, I had a question about the predictability work when you're showing the correlation formula. Yep. No. Yep. This one. So
I hope you're not going to ask me about the denominator.
Yes. Exactly. So if the expectation of your time series is 0, then the P actually cancels out, right?
Yes.
So what's the explanation for that? Because I can always kind of try to normalize my time series so they have an expectation 0.
No, we have actually, I don't remember how we've actually thought about that, and so there's no simple solution. Actually, if you do the analysis for 0 center, mean centered, actually something changes. I forget the actual. I forgot. I need to talk to Andres again about but this also bothered us. But we actually do have the answer about if you normalize the time series, you're actually removing actually also like the answer. I mean, I cannot reproduce the actual thing, but it hinges on the fact that sampling. Actually, when you're sampling from this, it actually will change the sampling as well. But sampling introduces basically correlated noise into your answer. So that's why it's like this whole, like you cannot sample from 0 correlated mean shifted things because somehow affects the whole systems. But I forgot the mathematical details. I can't reproduce them right now.
All right. Okay. Thank you. Maybe we can chat about it later too at some point.
Thanks, Kristina, and thank you for a great talk. And we'll see you all, I guess, in the next year, right?
Great. Well, yeah, thanks everyone. Okay. All right, bye.